Today it's my great pleasure to introduce Dr. Chris Hales. He hails from Sydney too and was at the same university I was at, so that must be a good thing. I'm not going to go through all the stuff there, you've got it on the little things. With that, I'll just ask you to welcome Chris Hales.
Thank you for that introduction, and thank you everybody for coming along. It has been 110 years since magnetic fields were first detected in space, in sunspots on the sun. Now, in this talk, I will take you on a tour of magnetic fields, highlighting what has been found and extending into the depths of interstellar and intergalactic space. But before we depart, I would like to spend a bit of time examining what exactly is a magnetic field. Many of you will have performed this experiment when you were young, where you take a bar magnet, you put it under a piece of paper, and you sprinkle iron filings on it. And this illuminates these otherwise invisible magnetic field lines that extend in loops around from north to south poles and south to north poles. If you take out a compass, then the needle of that compass will align with the magnetic field lines. The magnetic field itself will extend out to infinity, dropping off in strength as it does, and exerting less and less torque on the needle of your compass the further that you move away. For a long time throughout history, people had no real idea what caused this. Perhaps there's something special about iron. Maybe there's some kind of unseen particles circulating. But magnetism is actually generated by electric currents. And what you're seeing here is a coil, just a loop of wire. You can't see the underside, and iron filings sprinkled on a piece of glass in the middle, and it illuminates these otherwise invisible magnetic field lines that are running through the middle of this coil of wire. Now this is important because outer space is filled with electrically charged particles, a plasma, where you have electrons ripped off the nuclei, becoming positively charged nuclei, ions, and space is filled with this matter. Now, the motion of charged particles can both sustain and also cause the deflection. The motion of charged particles can generate and sustain magnetic fields out in space. So if you only take one thing from this entire talk, it is that this on the right-hand side is what magnetic fields look like in space. This is what cosmic magnets look like. There might be a wire out there, but there are electrically charged particles going around and around magnetic field lines. And this exists inside of planets, it exists inside of stars, it exists out in the depths of space. Now I could simply leave it at that and start showing you some pretty pictures and talking about numbers, but I want to delve a little bit deeper to give you a better feeling for how our understanding of magnetism has developed over history. And I think this will give you a much better grounding for interpreting what I'll be showing you later in this talk. Magnetism has been known about for over 2,500 years, the name originating from Magnesia in ancient Greece, where magnetized rocks were discovered known as lodestones. These rocks were likely magnetized as a result of lightning strikes. This was followed by the invention of the compass in China and used for navigation on the Earth ever since. But our story really begins in 1600, when William Gilbert published what became the most rational and experimentally evidenced investigation of magnetism in history up until that point. It's a fascinating read, all the more interesting because he chose to confront head-on the misinformation about magnetism that existed in his time. And he included phrases in his work such as pretenders to science, idiots, and this gem, may the gods damn all such sham, pilfered, distorted words which do but muddle the minds of students. So imagine getting that past a scientific referee today. His work is well worth a read, and there is a copy on display in the RAS archive, which has been kindly put there for you to have a look at after this talk if you're interested. His most profound experiment was to take a lodestone and to shape it into a little sphere. And then see how a compass moved when it was pointed as it was moved around this little sphere. And from this, he deduced that the Earth is like a little bar magnet. Gilbert's work explained why compasses tend to actually point down into the ground near the north or the south magnetic poles, rather than just simply towards the north or the south level with the Earth. But it would be hundreds of years before the cause of the Earth's magnetic field was understood. We'll return to how that works a little bit later. The early 19th century saw dramatic discoveries that would change our world forever. In April 1820, Hans Ørsted made what turned out to be a really critical discovery, and that is that a compass needle placed next to a wire showed a deflection when the current was turned on or off. So in the little picture at the right, there's a current running through that wire. If you sprinkled iron filings around it on a piece of paper, you would see these circular patterns. No longer were lodestones necessary to create magnetism. Now you could do it in the laboratory. Then entered Michael Faraday, who at age 20 got his start as a scientific assistant working at the Royal Institution just around the corner from here. In 1831, he extended on Ørsted's work by wondering, if a current can produce a magnetic field, can a magnetic field induce a current? The answer was yes, but instead of just having a stationary magnet, he actually had to move the magnet. So imagine if you had a coil of wire not connected to anything, you would have to move the magnet in and out to generate current in that coil. This was the discovery of electromagnetic induction, a concept that, as we will see, is fundamental to enabling an understanding of cosmic magnetism. It also led to the ability to generate electricity, which is handy. But Faraday wasn't done yet. Perhaps his most profound discovery was yet to come. But to understand it, we need to take a quick detour to explain polarization. Light is an electromagnetic wave that can be polarized. So light reflected off a surface, like a mirror or water, is linearly polarized. And so if you wear polarized sunglasses, this is why it works particularly well near water. It reduces the glare coming off the water because that's polarized. Now, polarization can be described in a few ways. One of these is linear polarization, and the way to imagine that would be if you tied a piece of rope to a pole and you shook it up and down like this. It's predominantly polarized in this orientation, this angle. If you shook it the other way, it'd be oriented at 90 degrees. You could do 45 degrees, whatever you like. You can also explain polarization in terms of circular polarization, where you can rotate your rope one way or the other way. So that's a quick primer into polarization. So now let's get back to Faraday's big discovery. On the 13th of September 1845, he performed an amazing experiment using a piece of glass which he had doped with lead. He was trying to do some experiments to make really high-quality optical glass for navigational instruments. And he passed a beam of polarized light through the glass while subjecting it to a magnetic field. When the magnetic field was turned off, the polarized light came out just the same as when it went in. But when he turned on the magnetic field and he made sure that the magnetic field was aligned along the direction that the light ray was coming, the state of polarization had been changed. And it turns out it had been rotated. And the amount of rotation of this plane of polarization is related to the strength of the magnetic field that was running through the piece of glass at the time and the amount of glass that the light had passed through. Now, it turns out that this effect makes for an extremely powerful probe of magnetic fields in space. And we'll return to this point again later in this talk. And as the comedian Sarah Silverman would say, let's put a pin in that. We'll come back to that. Faraday's experiment was the first evidence that light and electromagnetism and magnetism are related. And it led to him introducing the term magnetic field into the scientific lexicon. So this was a monumental finding that could have easily escaped detection. But to mark this milestone, he concluded his diary entry that day by saying, "I've got enough for the day." The Royal Institution has very kindly lent us his diary and a sample of the glass that is taken from the original ingot that he was using to perform this experiment. And that is also being displayed right now in the RAS library if you want to go and have a look at it after this talk. Now, Faraday was an exceptional experimentalist, but without any training in mathematics to the point of being mathematically illiterate, it would take someone with exceptional mathematical abilities to place electromagnetism into the concise and powerful language of mathematics. And that person was James Clerk Maxwell. So he took the relationships between electricity and magnetism of the time and put them into 4 really beautiful equations that describe how electric and magnetic fields arise from electric charges and how they evolve over time. They're so important that I'm going to briefly describe them now in words with no mathematics, presenting them in a lucid form that I've borrowed from the excellent writings of Professor Stephen Blundell from the University of Oxford. The first says, whenever you see an electric charge, electric field lines will be diverging towards it or away from it. So this divergence just tells you, how much charge you have in the middle determines how many lines you have coming in or out of that region of space. The second of Maxwell's equations says that there are no places where magnetic fields start or stop. They only ever exist in loops. There are no magnetic charges, not like with the previous picture where I showed you coming in and out of charges. There are no magnetic monopoles. If you chop a bar magnet in half, it's got a north and a south. You don't end up with a north and a south. You end up with a new little bar magnet which has a north and a south and a north and a south. The next one says, really represents Faraday's law of induction, electromagnetic induction, which says that if you're changing the magnetic field, then you're creating this circulation of electric field. And the final one is a mathematical description of Ørsted's work that was eventually put in mathematical form by André Ampère. Now, from these equations, particularly the last two, you can see that if you somehow energize an electrically conducting fluid, and you get some kind of circulation of electric field, then you can lead to a changing magnetic field. And if you somehow twist that up, you might be able to get a circulation of magnetic field, which in turn produces a current, and this whole thing might be able to feed off itself. Now, if you stop stirring your fluid, you wouldn't be providing any more energy into it, and the motion would stop and the magnetic field would die away. But what if there was a way that you could stir this fluid in just such a way that it would lead to an enhancement of the magnetic field? This thinking ultimately led to the concept of a self-sustaining fluid dynamo being developed 50 years later by Sir Joseph Larmor. So in a short but impressive talk, Larmor proposed an explanation for terrestrial and solar magnetism. The idea is that motions of a conductive fluid can enhance magnetic fields. This was the birth of the self-sustaining hydromagnetic dynamo. It would take another 50 years before the theory had developed enough mathematical muscle to describe what is now known as mean field dynamo theory, with much of this heavy lifting taking place behind the Iron Curtain in the 1960s under the leadership of Max Steinbeck. So why is it called mean field theory? Well, because in the analysis, what you do is you say, okay, I'm going to split my magnetic field properties up into some large-scale, smooth component and some small-scale, turbulent, fluctuating component. And an analogy would be, if I asked you to go for a walk across a mountain range and tell me what the average slope was as you were walking. Well, at any point, you might say, oh, look, it's very steep here and I'm climbing up a mountain here. But on average, there is some mean field slope to it. And so this is the essence of that. So if you want a takeaway point, in real three-dimensional fluids, mean field dynamos are able to take a small-scale turbulent flow and produce out of that some kind of large-scale coherent mean field flow. So what you're doing is you're extracting order out of chaos. So dynamo theory is a cornerstone of our understanding of cosmic magnetism, and it's still very much an active area of research in all aspects of astrophysics. This is particularly the case because it involves really challenging aspects of understanding turbulence in flows, and these are very computationally challenging things to deal with. Now, the type of stirring motion that you make matters. Not just any kind of stirring will create a magnetic field that will grow. But in general, there are some properties that all of the different varieties of dynamo theories require. And this is, you need some electrically conducting fluid that's in some environment that's rotating, and that environment is somehow also stratified, layered in some way. So this makes it applicable to planets, stars, and galaxies. So let's see if we can use dynamo theory to understand the Earth's magnetic field. So planet Earth, as Gilbert deduced, is like a giant bar magnet. We have an atmosphere that is protected by our magnetic field. The magnetic field strength at the surface of the Earth is something like half a Gauss, named after the 19th century polymath Carl Gauss. The magnetism inside the Earth can be explained by a dynamo, where electrical currents inside the liquid outer core of the Earth are being churned up. And the electrical currents are churned up because of heat, so convection coming off the really hot solid inner core, so it's providing some kind of radial type flow, within a rotating environment. And so you end up with these helical type of current patterns, and that gives rise to an overall magnetic field of the Earth. Now, before we venture out further into space, some of you might have noticed by now that an energy source is required to explain dynamo magnetism and dynamo-generated magnetic fields. But for the Earth, this seems to work, but what about a bar magnet? There's no battery connected to it, so where's it getting its magnetism from? So for this, we're just going to take a quick detour into the quantum world. Weird things happen in the quantum world, as I'm sure you can imagine. For one, electrons can orbit their nuclei without losing any energy, like a little current that just never loses energy. There's a remarkable theorem called the Bohr-van Leeuwen theorem, which states that magnets cannot exist if you only use classical physics. That is to say, you cannot do it using a system of moving electrical charges. You need quantum mechanics to do it. And the quantum mechanical property that produces magnetism is known as spin. Infinitesimally small electrons act like tiny little bar magnets due to this spin. Now, it turns out, to make a permanent bar magnet work, the spins of all of the electrons need to be lined up in the same direction. The mechanism for doing this is known as the exchange interaction. And what this does in materials like iron is it favours spins to be aligned because that will minimise the electrostatic repulsion between the electrons in neighbouring atoms. And this esoteric aspect of quantum mechanics will be familiar to any parent who knows that to minimise your own energy, you never put two bickering children next to each other at the dinner table. You always want to put them further apart. So that's the exchange interaction. So the next time you look at your fridge magnet, you'll know that it demonstrates quantum mechanics. You cannot have a fridge magnet in classical physics. That's quite amazing. There's much more that could be said about solid-state magnetism, but I'll say just one more thing. Paul Dirac, who has a very famous equation that he developed in quantum mechanics and predicted antimatter, which was eventually observed, also predicted the presence of magnetic monopoles. So these are sort of the magnetic equivalent of an electric charge, where you have lines coming out of a north pole and going into a south pole, which I previously said couldn't exist. They've never been observed, but in 1982, which was the year that Thomas Dolby released his classic hit, She Blinded Me with Science, just to put it in context, there was an amazing experiment that claimed to detect magnetic monopoles, though this has never been reproduced since. Now, it turns out that if there is just one magnetic monopole anywhere in the universe, then this will explain why electric charge comes in discrete units. You can't have half an electron charge in nature. So now let's return to our classical world of dynamo theory operating with electric currents, and let's take out our compass and venture out into space and see if we can understand the cosmic magnets that we encounter. Ah, that was the previous point. So we can take spacecraft out and fly them around the planets in our solar system and see which ones have magnetic fields. And doing that, we've been able to find that the 4 outer gas giant planets, Jupiter, Saturn, Uranus, and Neptune, all have strong magnetic fields, which are all powered by dynamos, this churning of fluid inside their cores. It turns out Mercury also has a magnetic field, though it's a lot weaker and it's a bit more chaotic. There is no global magnetic field has been detected around Venus or Mars, and which means that there's no dynamo operating in these planets. The reason for Venus is thought that conduction is inefficient, so the stirring motions just aren't quite right within Venus. And in the case of Mars, its inner core has cooled down to the point where, again, the motions of the particles, the electrically charged fluid, is not able to sustain a magnetic field. Now, Mars is interesting in that it probably had a dynamo early in its history, because the rocks that are on the surface of Mars show evidence of being magnetized. If you take a compass to them, you could see that they are magnetized. And last year there was a really interesting finding, which was that the magnetic field lines from the surface of Mars were actually found to extend out and not just loop back to other rocks on the planet, but extend out into interplanetary space and reconnect with the solar wind, the solar magnetic field, as it's being driven out into interplanetary space. And so imagine navigating with a compass on Mars there, going up into the sky. Now, we can also infer magnetic field properties of planets beyond our solar system. Last year, there was a particularly interesting example of using the weather on a distant planet to learn about its magnetic field. So this is a Jupiter-sized planet located 1,000 light years away, and it was discovered in about 2008. Now, if there were no winds on this planet, then the hottest point on the planet would be the substellar point, the point that the star is lighting up this planet, and that would be the hottest point. Now, it happens to have very strong winds, and so the hot spot is actually shifted east of the substellar point. But the really weird thing about this planet was that every now and then, the hotspot would end up on the west of the substellar point. And the reason for this was a mystery. Why is this happening? So my colleague, Tammy Rogers at Newcastle University, investigated this and figured it out. And she performed magnetohydrodynamic simulations, shown here, and found that magnetic fields can affect the weather patterns on this planet so much that they can make the wind turn around from a planetary system, turn around and start going back in the other direction in various places. Now, her analysis set a minimum strength of the magnetic field on this distant world of 10 times the magnetic field strength that we would see here on our planet Earth, which I think is really quite remarkable, given that this thing is 1,000 light years away, and all that was done was to look at where the bright point is on a distant planet. I think that's quite an amazing achievement. So now let's turn to larger objects, stars. 110 years ago, George Hales made the first measurement of magnetic fields in space, looking at sunspots. And he used a technique called Zeeman splitting, which involves looking at how light, the specific colours of light, gets split into different colours of light with opposite circular polarizations when the light is coming from a region with very, very strong magnetic fields. And if you see this splitting of the light into different colours, then you can deduce what the magnetic field was in situ at that particular location. And so might be a little bit hard to see, but this is showing a sunspot. There's a little slit where light has been let through, and here is showing you what happens if you spread that light out according to the different colours of light, and there happens to be this dark band here which gets split into these different lines right here. And that splitting, you can use that to deduce the strength of the magnetic field in the location on the sunspot on the sun. So this showed that magnetic fields are around 3,000 times stronger than the rest of the surface of the sun when you're in sunspots. The concentration of the magnetic field there makes the region of the sun cooler, and that's why that part of the sun looks darker. Larmore's pioneering work in 1919 was on the self-sustaining dynamo was directly influenced by this result. Oh, and there's Peter Zeeman there. So the Zeeman splitting technique is actually based on the last experiment that Michael Faraday was working on before his death in 1867. And Zeeman was curious about completing Faraday's work, and so he thought, I'm going to use the equipment in my laboratory to see if I can make this work. But that happened to be against the wishes of his supervisor at the time, and he was fired. But I think it's safe to say that it was probably worth it, because a few years later, in 1902, he was awarded the Nobel Prize for that effort. Now, the sun is powered by a dynamo with many details that are still being worked out to this day. It exhibits all kinds of really interesting magnetic behaviour, such as solar flares, which are these big magnetic loops that are flung out into interplanetary space. It turns out other stars do this behaviour too. So an interesting finding that's just come out last year and this year is that Proxima Centauri, our nearest star beyond the Sun, located 4 light years away, exhibited a huge flare in March 2017. It became 1,000 times brighter and then dimmed again, all within the period of 2 minutes. Now, given that Proxima Centauri hosts what is an otherwise seemingly habitable planet, then that was announced to much excitement, which many of you probably recall in 2016, then this unfortunately deflates much hope for finding life on the planet around Proxima Centauri. Magnetic fields can be dangerous things. So as long as we're talking about dangerous things and in space, then I think it's time to follow our cosmic compass out to nature's most powerful magnets, magnetars. Magnetars are the collapsed cores of large stars, around 10 to 30 times the mass of our sun. And they're a type of neutron star, which means they're mostly made up of neutrons, but they also contain protons and electrons, charged particles that can maintain the magnetic fields from these environments, from these stars. They contain the mass of a sun within a city-sized diameter of only about 20 kilometres. They're really extreme objects in nature. But what's really interesting here is that their surface magnetic field strengths are enormous, of order 10 to the 15 Gauss. Now, to put that in comparison, that is 1 billion million Gauss. And here on Earth, the strongest magnetic fields that we can produce are only 10 million Gauss compared to 1 billion million Gauss. And those 10 million Gauss come from experiments where basically you blow up your experiment. There's no equipment left. However, I think it's interesting to think about the way that the magnetic field strength drops off from a magnetar. It's exactly the same as the magnetic field strength dropping off from a bar magnet. The further away you go from it, the less your compass needle will be deflected by it. So if I'm standing right here on Earth with my compass that's aligned with the Earth's half a Gauss magnetic field, how far away would a magnetar have to be before it starts deflecting my compass here on Earth? Well, the answer is you only need to bring it within about 1.3 million kilometres. That's less than 1% of the distance between the Earth and the Sun. So that's pretty impressive for an object that's 20 kilometres across, but that's not going to affect cosmic scales. Of course, if you put a magnetar in our solar system, it would exhibit lethal flaring behaviour that would make Proxima Centauri seem very peaceful in comparison. So now it's time to take our compass out into deep space, into the interstellar medium of our galaxy and the Milky Way, other galaxies, and that of other galaxies, to find magnetic fields that are not going to die away after 1.3 million kilometres, but are somehow able to persist over huge, enormous galactic scales. If we could fly out of our Milky Way galaxy and go up and look top down, our frisbee-like Milky Way galaxy, it would look something like this, a face-on view. Our solar system, our sun, is located down there in the yellow point. There's a supermassive black hole located in the middle of our galaxy. Now, it would take light, which travels at 300,000 kilometres every second, it would take light 100,000 years to go from one side to the other. For comparison, light only takes a second to go from Earth to the Moon. It only takes a few hours to go between the Sun and the edge of the solar system. And it only takes 4 years to go between our Sun and Proxima Centauri, our nearest stellar neighbour. The vast majority of the Milky Way's volume is occupied not by stars, but by the tenuous depths of space that exists in between the stars, known as the interstellar medium. The interstellar medium is not completely devoid of matter. It's filled with plasma, these electrons and positively charged ions, but it's also filled with molecular gas and dust. And the galaxy is quite a dusty place. And it's that gas and dust, the molecular material and dust, that eventually condenses to form stars and planets, just like the one that we're standing on right now. So there's matter out there in interstellar space which can act as traces for magnetic fields. So let's have a brief look at some of these. This map shows you the full sky in a type of projection that you're familiar with. So imagine if we were looking at a world map, and you're looking down on the world, and you've got all of the countries, the landmass, and the water. Well, imagine now, instead of looking down on the map, you're under the map looking out. So this is showing you an entire map of the entire sky. And we're looking through our frisbee-like Milky Way galaxy. The centre of the Milky Way is located right towards the middle of this picture. And because this is a map of the whole sky, if I go from the middle to the very edge of the picture, that's like me looking in this direction and then looking 180 degrees behind me. And the image wraps around. So it's just like a world map, except instead of looking down, you're looking out. The map shows linearly polarized light that's been emitted by elongated and spinning dust grains that are spinning in the magnetic field of the Milky Way galaxy. And it reveals these really beautiful swirling patterns. But it's very difficult to get a sense of depth in this picture. You know, if I said, take me out to the galaxy and take my compass and which direction is it going to point in 3 dimensions, it's very hard to determine that from this kind of an image. So to try and address that, we can look at it in a different way. We can show you a reconstruction now of the Milky Way's interstellar magnetic field, resulting from Faraday rotation towards around about 500 pulsars. And these are neutron stars that are spinning like little lighthouses, and they're emitting polarized light. And so we can observe Faraday rotation towards them. Now, I think it's somewhat fitting that as Michael Faraday was particularly interested in showing that all materials in nature were magnetic in some way. And it's his magneto-optic rotation effect that is really the most powerful tool that we have for studying magnetic fields out in the depths of interstellar space. And astronomers have been able to make measurements like this and to measure Faraday rotation in space only since 1962, when the first observations were made actually from a telescope located in Australia. Now, to keep you on your toes, this map is actually rotated 180 degrees from before. The sun is now located at the top, but that doesn't matter. That's not an important point for this. The interesting thing about this is this pattern of magnetic field directions that's in the galaxy, where if you took out your compass, it would tend to point clockwise, according to where the red areas are, and counterclockwise where the blue areas are. And you can see that it almost looks like there's these field lines that are coming in around to the right side, around again, and then coming back out again in this blue pattern. And that's called a bisymmetric pattern. And this inference of a bisymmetric pattern is actually a really difficult thing to obtain and to tease out of the data, because it's very difficult to reconstruct the magnetic field of the Milky Way while you're actually embedded within it. A complementary approach is to try and look out at external galaxies and see if we can tease out any global common features in other similar galaxies. This is shown here in the galaxy M51, the Whirlpool Galaxy, and it's somewhat similar to our own galaxy. Using polarized light from this galaxy, astronomers can effectively sprinkle iron filings on it and illuminate its magnetic field lines. And this type of work again involves Faraday rotation. Now, from observations like these, astronomers have deduced that the strength of the mean field, this mean magnetic field in spiral galaxies, is around 15 microgauss. But this 15 microgauss extends coherently over tens of thousands of light years. Using the principle that I started the talk with. It's just charged particles spinning around. And something has energized these charged particles to spin around to create this beautiful coherent pattern that you see in this galaxy. Well, let's get a feel for this 15 microgauss number. So imagine the Earth is alone in the universe, and we're going to measure its magnetic field strength as we move further and further away from it, which we know is going to drop off, just like for a bar magnet. How far away from Earth would you need to travel before that half a Gauss field strength that we measure here on Earth drops away to 15 microgauss? The answer is only about 200,000 kilometers, less than a light second, halfway to the moon. What about from the strongest magnets in nature, magnetars? Here you would only need to travel about 40 million kilometers away, and that's about 2 light minutes. Yet somehow, in galaxies like this, our own Milky Way, and many other galaxies that astronomers have looked at, this kind of magnetic field strength is maintained over tens of thousands of light years. I think that's really quite remarkable. So how can we understand what is creating this striking display of magnetism in this big galaxy? Well, the answer comes back to dynamos. You've got a rotating system, you've got some kind of radial blasting motion provided by stars exploding, supernova explosions going off, and that combination of this specific type of stirring motion allows the mean field dynamo to wind up into this amazing large-scale feature that you're seeing right here. So in that way, it's very similar to how the convection and rotation within a planet or a star generates its large-scale magnetic field. But here it looks a little bit different, but it's the same mechanism operating. So that's all well and good, but which direction will your compass point in this picture? For that, I want to point out an interesting bit of history for galactic dynamos. Now, a very firm prediction from Dynamo Theory is that you should see an axisymmetric magnetic field distribution. The magnetic field should always be pointing in or always be pointing out. Now, some of you right now are probably thinking, wait, there's no magnetic monopoles. So if you're all pointing in, then that's going to a monopole. Well, I'm not showing you the third dimension of this galaxy, above and below the plane. And that's where the field lines go out, they come back around and they loop. But for clarity, I'm just going to show you the top-down view. Now, the axisymmetric pattern shown right there is not the only type of pattern that you will see in a galaxy. You will also see something called a bisymmetric pattern, which is one side coming in, the other side coming out, versus everything either going in, or it could also be the reverse of all of these situations. And these patterns will actually be superimposed on each other in real life, and so deducing from your data what it is that you're looking at, you can imagine is going to be a little bit tricky. So anyway, serious observations started coming out of galaxies and their magnetic fields in the 1980s, and what did they all reveal? Well, they all revealed the bisymmetric case. So there was a problem. There was a fundamental disagreement between observation and theory. Many people took this evidence over here to indicate that magnetic fields are actually forming and winding up a large-scale intergalactic magnetic field, something that existed out there before the galaxy had formed, and it was being wound up. And you can see that. Imagine if I pull those all taut, what you're going to end up with is just straight lines. And then basically as the galaxy winds up, you're winding up this pattern that you see here in the bisymmetric case. So there was a crisis in dynamo theory. Both sides thought that they were right, and both of them had very good reasons for believing in what they were finding. But it also took a really long time, a decade or so, for each side to really appreciate some of the subtleties in the arguments that each of the sides were coming up with. Now, the Faraday rotation observations needed to do these measurements are really tricky, and after much back and forth, it was found that there were subtleties in the way that the data was being analysed, and this was leading to the observers to claim the wrong result. When this was realised around the 1990s, all the galaxies that had been previously thought to indicate the bisymmetric case suddenly revealed the axisymmetric case. Not only was this scientific progress, but it led to much closer and more fruitful collaboration between these groups of theorists and observers. Now, I like this example because I think it demonstrates that in science, you need disagreement to make progress. It's only when you have to defend your convictions against really strong opposition that this will lead to insights. William Gilbert typified this, and so scientists really do need to push each other and disagree to make progress. I think that's an important point. One of the ongoing questions in galactic dynamo research is how these dynamos on galactic scales actually got started. There could have been very efficient small-scale type dynamo motions that were then somehow picked up by the big large-scale rotation of galaxies and wound up into the fields that we observe today. Or maybe those original observers were onto something. Maybe there was actually some intergalactic field. Maybe not as strong as they were originally thinking, but maybe there was an intergalactic field that has been wound up into the galaxies that we see today. So with this in mind, let's take our compass and head out to the ultimate depths of intergalactic space. And galaxies are not just sprinkled randomly over the cosmos. They are located in clusters, filaments, and voids. Clusters are where you have hundreds of galaxies that might be residing in particular volumes. Filaments are these places where you have galaxies sprinkled out in regions that connect between large clusters. And then there are also voids, regions where you have hardly any galaxies or none at all in these huge expanses in space. And this structure is thought to have been seeded very early in the universe through quantum fluctuations, which developed into more significant density variations over time and allowed some places to attract more matter and others less so. So this is just a time-lapse movie showing the evolution of cosmic structure. And if we would think how big the Milky Way would be, our entire galaxy, in the final panel down here, it would just be a tiny little dot. We're talking very, very, very large scales now. The intergalactic medium is the space in between the galaxies in this environment. Now, magnetic fields have been detected in intergalactic space inside the galaxy cluster environments, these more dense regions that you're seeing around here. First in the 1970s, but really since the 1980s. But what I want to focus on now is the much less studied filaments and voids. Now, despite a large number of attempts, there have been no unambiguous detections of magnetic fields in filaments and voids yet. So how could you get magnetic fields out into those environments is an important question. Well, there are three main contenders. The first are known as primordial magnetic fields. These would be generated very early in the universe, soon after the Big Bang, a few microseconds, minutes, hours after the Big Bang. And these magnetic fields would tend to fill the entire universe with magnetic fields that would then be present at the time when the first stars and the first galaxies were forming. The next main category, or main type, known as magnetic fields that arise as a result of pollution. So these are outflows from various objects. So you can have winds dragging magnetic fields out into intergalactic space from galaxies. You can also have supermassive black holes at the center of galaxies winding up magnetic fields and blasting them out close to the speed of light into these huge big plumes, polluting intergalactic space with magnetic fields. The third way that's been proposed that you could get magnetic fields out into the filaments and voids is that of cosmic structure formation itself. And here, as material in the light, if you remember from that simulation before, as the material is condensing under gravity, it wants to fall in, it will get hot in places, it will shock, and that process will tend to fill the places where a lot of this gas is accreting with magnetic fields, as shown in this simulation here, revealing this web, this cosmic web structure that I was talking about before. Now, if we want to put some numbers on the kind of magnetic field strengths that we expect in these environments, we know from observations that magnetic fields in the intergalactic medium in galaxy clusters are around a microgauss, similar to the types of levels that you see inside galaxies. But now we're talking magnetic fields that extend over huge scales in the intergalactic medium. The field strengths are expected to be around about nanogauss in the intergalactic medium within filaments, and the field strengths out in those voids could be very, very small indeed. They could be of order picogauss or even much, much less than that. We just don't know yet. Now, trying to measure magnetic fields in the filaments and voids of the cosmic web would provide us with the necessary fingerprints to then work backwards. So remember those three main categories. If we could measure magnetic fields out there, we could try and fingerprint the key physical mechanisms that put the magnetic fields there in the first place, and then that would give us insight, a new insight into the process of galaxy formation, galaxy evolution, and perhaps even give us a unique way in which to peer into processes that were taking place very early in the primordial universe, soon after the Big Bang. Now, this is one of my current research activities, where I'm performing the most sensitive search ever for Faraday rotation through the intergalactic medium. To observe Faraday rotation, we need to observe at long wavelengths. We need to observe at radio wavelengths, so that is to say, colours of light that your eyes cannot see. So my project requires making the most sensitive image of the sky ever at radio wavelengths. And the reason for this is we want to pick up lots and lots of very faint galaxies that are emitting polarized light, and then look at how that light gets influenced as it passes through the filaments in the cosmic web. To do this, I'm using the world's most powerful centimetre wavelength radio telescope known as the Carl G. Jansky Very Large Array, located in the US and named after the first person to detect radio waves from space in 1931. This is a multi-year project, and by next year I'm hoping to get the final bits of data, and I really look forward to seeing what they reveal. I could detect nothing, in which case I'll be able to place some really good constraints on the strengths of magnetic fields out in the filaments, the intergalactic medium in filaments and voids in large-scale structure. Or maybe it could lead to a detection, in which case, at the end of the day, I can write into my diary, "Have got enough for the day." And with that, I'd like to acknowledge the support of my colleagues from around the world, especially those at Newcastle University. I want to thank the RAS for this opportunity to speak today, and I'd like to thank you all for listening. Thank you.
Well, a lecture which was all new, and I'm sure all of you will be thinking up questions. We have a few minutes of questions, about 10 minutes of questions, and there's a microphone which will go around. So can I have the first question? I mean, think fast, please. First question, yes, over here. Thank you.
You mentioned magnetic fields in spiral galaxies, which have sort of ordered rotation. What happens when you have a galaxy with no ordered rotation, such as an elliptical or an irregular?
That's a very good question. So people have been looking for magnetic fields in, and have detected them, and coherent large-scale magnetic fields in a whole range of different kinds of galaxies, even ones that look like they're train wrecks. You shouldn't have any kind of large-scale fields being presented in these environments. But it comes back to the type of flows that you can stir up. And the mean field dynamo, I was describing a general dynamo. There are lots of different types of varieties, and so right now that's actually an active question as to investigate how it is that different types of galaxies, dwarf galaxies, irregular-looking galaxies, how it is that they can generate and maintain magnetic fields. The question about elliptical galaxies, these big galaxies that don't have spiral structure, they're just this big dispersed mass of stars going in all sorts of different directions. No one's been able to measure magnetic fields in those environments because the density of the interstellar medium in those environments is so tenuous that there's very little tracer to act upon. And the hope is that with new telescopes, and in particular new radio telescopes that are coming up over the horizon, they would give us an opportunity to study these really interesting environments. So yeah, thanks for that.
Hi. That was a lovely talk. Thank you very much. Just wanted to know, in relation to black holes and the magnetic field, and how does that affect the galaxies as well? Because obviously it's a churning movement, and the quasars, obviously. So does that have a big effect with the magnetic fields?
Thanks for that. Black holes affect lots of things to do with galaxies, and as I showed in that one of, I don't think I have it on that slide, there was an example of a black hole spewing out magnetic energy into intergalactic space. If that was going off in the center of our galaxy, we probably wouldn't be here. They inject a lot of energy. The magnetic field that arises from these environments comes from material that is being entrained as it forms an accretion disk around these black holes and then gets blasted out. The impact of that on the large-scale magnetic field is probably not going to be particularly extreme. There's examples of colliding galaxies coming in, and you can see the large-scale magnetic field is somewhat decoupled from what's going on in the central regions. But they do play an enormous role in terms of blasting material out and doing other kinds of dynamic things to the galaxy.
Right. Over there, please. Yeah.
Gravity is known to warp space. Is there any indication that a magnetic field can warp space?
The thing that warps space is energy being located in various environments. So matter is a form of energy, E equals mc squared. And so the presence of anything in any volume of space, any matter or charged particles or magnetic fields, they contain an energy density to them. And so in that respect, the answer is yes. They do actually cause an effect on space-time. But in terms of actually affecting the motion of particles under the force of gravity, it really depends on whether the particles that are coming and channeling around are charged or not, because it's only the charged particles that will be affected by the presence of a magnetic field. And the neutral material and the charged material may somehow be intermixed, and that could cause that to be diverted in that manner. But if it isn't, then probably not.
Thanks very much. Coming down to the materials level, right at the very beginning, if you take an iron bar and you wrap it in a coil, pass a current, you make you make a bar magnet. You take away the coil, and it's still magnetized. Something's happened to the internal structure of the iron. How does that work? But if you then go on to drop the magnet, you begin to demagnetize it. How does that work?
Good questions. So, magnetism in solids is to do with the alignment of electron spins. And anything you do to disrupt that alignment will destroy your magnetism. So there's a thing called the Curie temperature, named after Pierre Curie, Murray's husband. And incidentally, it was actually Marie Curie, her pre-PhD work was in looking at magnetism of steel, and that's what actually brought her and Pierre to meet each other for the first time. That Curie temperature is to do with if you make a material hot enough, it will lose its magnetism. Similar to how if you drop a material, it will lose its magnetism. So what you're doing is if you're dropping it, you're introducing energy into the system and you're disrupting the domains where all of the electrons have been lined up. Going to your first question, which was, did you say if you take away the coil? So there, it's to do with how the type of material that you're using in your electromagnet. And so for some materials, this exchange interaction is a really strong feature. In iron, it's particularly strong, but in other materials, less so. And so there are materials which will tend to allow the electrons to remain aligned as long as there's something that's giving some energy to them to remain aligned, but as soon as that is taken away, then other aspects come into play and the alignment of those spins goes out and you lose your magnetism.
This is one here.
I'll just show. Is there any reason why dark matter can or cannot be charged or produce a magnetic field?
Oh, that's a tough question. Nobody knows what dark matter is. So, yes and no.
Good answer there. Right, somewhere else? Yes, over here, please.
Shout also perhaps. You're talking about the interaction between the currents and the fields and so on at the planetary level, at the cosmic level. When you're talking about the solar level, you were slightly quiet about it. Can you say a bit more about the MHD effects of things on the surface of the sun and flares and all that sort of thing?
That's an incredibly complex. I mean, I had to pick material, obviously, to focus on. What causes the magnetic field features from the sun is still being actively worked out, and there have been really interesting findings recently to do with the types of waves that can exist on this, in the sun, and how this might relate to the solar cycle that we're seeing and what kind of flaring behaviour you have. But I don't think that it's safe to say that this process has been fully understood yet. There's a question to do with what actually causes the magnetic field generation on the sun. Is it to do with the convection, this bubbling away, or is it actually to do with processes happening deeper in the sun in the radiative regions, or particularly it's something called the tachocline, which is this interface between the radiative inner zone and the convective outer zone. And a lot of those details are still being worked out, and you know, it remains to see how well they can explain all of the phenomenology that we see from the sun. Sorry, I can't answer that better.
There's a question here. Yes, please. Yeah.
Well, I can show as well.
Right.
Could you comment please on the existence of magnetic fields in places like Europa and Enceladus?
Not particularly. The one thing I can point out is that the only planet in our solar system, the only moon in our solar system known to have an active dynamo on it is Ganymede. And there is a planned mission from the European Space Agency to go and visit this planet. So in the next few years, I believe it might be launching in 2 or 3 years, and then soon, a few years after that, some interesting findings might be resulting from that.
Right. If there isn't a pressing one, I think we've just fantastically chimed 2 o'clock. Brilliant. So thank you very much again for all